Light, that is, visible infrared and ultraviolet light, is usually described as though it is a wave. We talk about light being a form of electromagnetic radiation, which travels in the form of waves and has a range of wavelengths and frequencies. Blue light has a smaller wavelength, red light has a longer wavelength. So we know that light has properties of waves. But at the beginning of the 20th century, scientists had begun to question the wave-like nature of light. They had found new evidence to suggest that light was not really a wave, but more like a particle. To solve the problem, famous scientists like Einstein, Hertz, and de Broglie had to put their heads together and come up with a better solution for how to think about light. Their contributions led to the current scientific theory of wave-particle duality. Scientists have known for a long time that light exhibits wave-like behaviors. Many of the things that light does are only explained sufficiently by thinking of light as a wave. Refraction and diffraction are two examples. Light refracts when it travels from one medium to another because waves travel at different speeds through different media. In a similar way, light diffracts when it travels between or around objects because obstacles make the light waves bend. So obviously, we're not wrong about the light behaving like a wave. We even use the wave diffraction of light by reading interference patterns in X-ray crystallography. If you need more evidence that light acts like a wave, just think about the Doppler effect and how it affects our perception of light. When astronomers observe distant galaxies, they notice a blue shift in the galaxies moving toward us and a red shift in the galaxies moving further away. The apparent change in light frequency is due to the way motion affects the traveling waves. Waves on the front end of a moving object get bunched together. Waves on the tail end of a moving object get spread apart. We already know the Doppler effect occurs in sound, and sound is definitely a wave. So if the Doppler effect occurs in light, then light has to be a wave too, right? Scientists began questioning the wave-like nature of light when they first discovered the photoelectric effect, which describes the way electrons are excited and emitted from matter when they absorb the energy from light. In 1887, Heinrich Hertz observed that a charged object would create a bigger, faster spark if it was treated with ultraviolet light, because the light was actually exciting the electrons. Further studies by other scientists showed that electrons really could be knocked out of a metal in response to a beam of light. For a while, scientists thought the electrons were just absorbing the energy in the light wave and then using that energy to jump out of the metal. The more energy the electrons could absorb, the more energy they could use to jump out. But it turned out it wasn't that simple. Scientists tried increasing the intensity of the lights on the metal. They figured that a greater light intensity would give more energy to the electrons, making them jump from the metal to a higher energy level. But that didn't happen at all. Instead, the electrons were emitted at the same energy level as before. There were just more of them. Scientists realized they were wrong about their theory. If light was really a wave, then the energy of the electrons should have increased, not the number. The electrons were not absorbing energy in a way that matched our wave theory of light. So if light wasn't really a wave, then what could it be? Albert Einstein thought up a good solution to this problem. In 1905, he suggested that we should sometimes think of light as a particle instead of a wave. He said that if we imagine light to exist in little packets of energy, then all of our observations make a lot more sense. Think of that beam of light as though it were a stream of tiny energy packets. Each packet has a mass of 0, so it doesn't weigh anything. Each packet contains a certain amount of energy which it can transfer to the electrons when it strikes the metal. Einstein called these packets light quanta, but now we call them photons. A photon is a nearly massless particle carrying a small amount of energy. We use photons to quantify or measure the amount of the energy in light and other electromagnetic waves. Each photon can excite only one electron at a time. When the intensity of light is increased, then the number of photons is increased, so a higher number of electrons are knocked loose from the metal. The energy of the electrons doesn't change, because the energy of each photon is still the same. Einstein's revolutionary idea about photons wasn't really confirmed for many more decades. But nowadays, photons are a major component of how we study light and subatomic particles. So photons are fine for describing light when it comes to small-scale behaviors like the photoelectric effect. Maybe light really does exist as a stream of massless particles. But what about all those wave behaviors we talked about? Refraction, diffraction, and the Doppler effect don't make sense if you think of light in terms of photons. They only make sense in terms of waves. What's a scientist to do with all this conflicting evidence? Louis de Broglie came to the rescue in 1924. He theorized that every moving particle exhibits properties of a wave. This was later called the de Broglie hypothesis, but it's generally referred to as the theory of wave-particle duality. Wave-particle duality means that all matter has properties of both particles and waves. So we can think of light as a wave sometimes and as a stream of particles or photons at other times. But it's not only light that gets the fun of being both a particle and a wave. Duality theory applies to bigger things like electrons, atoms, and molecules. It may even apply to objects as large as bacteria. So by saying that all matter includes both wave and particle properties, de Broglie basically took two competing theories and rolled them into one. Wave-particle duality is still a theory that doesn't quite explain everything in physics. Scientists are still working at the kinks, and it may be that someday we change our minds about the theory. But for now, most scientists agree that de Broglie's hypothesis sufficiently explains the observations we have made about waves, photons, and electrons. All matter can be described in terms of particles and in terms of waves. Light behaves most obviously as a wave, but there are some instances where it acts like a stream of particles in the form of photons. Visible light and other types of electromagnetic radiation are usually described as waves. Refraction, diffraction, and the Doppler effect are all behaviors of light that can only be explained by wave mechanics. The wave theory of light was challenged when scientists discovered the photoelectric effect. Light was observed to excite the electrons in metal so that the number of electrons was proportional to the number of light quanta, or photons. This suggested that light was really a stream of particles, not a wave. Today, scientists embrace the theory of wave-particle duality, which means that all matter has properties of both particles and waves. The theory has been proven for light and subatomic particles, but we're still working out the details when it comes to larger objects.